Thanks, Fred, for the introduction, and thanks for the invite. So today I'm going to talk about a new area that this is my first work in this space. I'm excited to talk about this. It's a problem I spent quite a while working on with a bunch of different people, and finally we have some solution. So this is going to be beyond worst case sequential prediction, and we're going to talk about how to get beyond worst case using this idea of abstention. This is joint work with Steve, Shai, and Abhishek. The problem we're going to look at is sequential prediction. So we're given a data that comes to us in a sequential manner, so x1, x2, so on till xt. And at every time, there's an algorithm that has to decide what to predict, and the predictions are going to be denoted by this y hat. And then the world will provide us with a true label of what the actual label should have been. And the learning algorithm will suffer a loss based on the mistake that the algorithm makes. And for this talk, I'll assume that this is going to be a realizable setting, that there's going to be some hypothesis from a function class f that the true label is always given from. Okay? And the goal here is to minimize regret or error, which will be the total number of mistakes made by the algorithm. And the hope is that as t goes to infinity, the number of mistakes go to 0. And at that point, we say that this is a good algorithm. So there are two ways generally these online learning algorithms, sequential prediction algorithms are studied. So the left side is the very nice case, which is a stochastic sequence case, where we assume that the input sequence, the data that is generated x1 to x3, is drawn IID from some unknown distribution D, and there's no change in that distribution is fixed. On the other hand, there is the worst case, which is like all bets are off. We have no assumption on how the data is generated, and at every time step it could be generated by an adversary that has knowledge of the algorithm and the history that we have. So generally in the first case, it's easy to get strong results. And because the sequence is stochastic, we don't have to be adaptive to change in the distribution, so we can get good results there. But however, this model is very simplistic to model real-world situations, because in real world, we don't expect all the data to come from some unknown fixed distribution and not changing over time. Whereas if we go on this worst case side, this is too pessimistic, because every data point can be adversarial, and here it's really hard to get good results. And but on the positive side, this is a very robust model, because you're robust to all kinds of changes and attacks. And here, just for the complexity notions that come into play in these settings. So in the stochastic sequence setting, the complexity depends on this notion of VC dimension of a function class, the function class f that the labeling function comes from. And on the worst case, this complexity depends on the Littlestone dimension of the function class. And generally, the Littlestone dimension of the function class is much, much larger than the BC dimension. And for instance, even like the simple instance of learning a threshold on a 1D line has infinite Littlestone dimension, and only the BC dimension is 1. So they're like arbitrarily far apart. And the hope is that the real world kind of somehow behaves in the middle of these two settings. It's not really worst case, and it's not really stochastic. So how can we get results that are more of the stochastic nature, but can handle adversarial? So this is going to be the main question that we're going to try to answer, that how can we design algorithms that achieve stochastic-like guarantees, however being robust to some notion of adversarial data. And here I'm going to today present a new framework that sits between the stochastic and purely stochastic and fully adversarial setting, and then discuss some new robust algorithms that we get in this setting. And the key idea that will be underlying this whole thing is that we're going to try to design algorithms, and the model will actually necessitate that we want to always make predictions with certainty. So we can, whenever we're making predictions, we want to make good predictions, and otherwise we're okay to abstain from making a prediction when we have adversarial data. And I'm going to talk about what I mean by this in the subsequent slides. So let me start with part 1. So this is going to be defining the model, and this is sequential prediction with adversarial injections and abstentions. I'm going to decode all of the words that I have here. And feel free to interrupt me and ask me any questions. And I need to add an acknowledgement that when I started working on this problem, this idea of this model came with discussions with Theodoros and Adam. But eventually, we worked with other people to actually get algorithms for this model. Okay, so let's get back to our sequential prediction model. So this is the model that I discussed before. We have data coming to us one at a time, and we're making a prediction at every time step. What we're going to add here is adversarial injections. So instead of the data just being always, we'll assume that the data is stochastic. There's a true stochastic stream where the data is coming from, which means there's an underlying distribution that the data is drawn from. And there's an adversary in play, and the adversary at every time t decides that whether it wants to inject an adversarial example at that point. And then it can inject that adversarial example, and here I've denoted that by color red. I don't know if it's visible, but that's an example that the adversary adds. The only thing is that the adversary has to decide whether to inject the adversarial example before it sees what the true IID example would have been. So that's why it's called injection, that you're injecting an example into the stream. And you can think about this as like an adversary, like for instance, the adversarial examples in vision models, that there's an adversary that adds in an example. It can't change, it doesn't get access to what the true distribution was generating, it's just adding an example in the middle. Okay, so this is what the model is with the adversary injections. Now, of course, the adversary could just inject all the examples and the stream could be fully adversarial, right? So it interpolates between completely stochastic to fully adversarial, depending on how many injections the adversary wants to add. So clearly we know that if the stream was fully adversarial, we would again go back to the fully adversarial setting. So we really can't hope to do better without adding some extra thing to make this model beyond worst case, okay? So what we add here is this option that the learner, the algorithm has. And the option that the algorithm has is that the algorithm can decide to abstain on predicting on some inputs. So instead of always choosing to predict this y hat t being say 0 or 1, which are the two labels, it can decide to abstain. And this will be denoted by this bot operator. So basically you can decide that, okay, I'm not going to make a prediction at this particular time. And this is the extra property that we have. Again, you would think that this makes sense because maybe it's too hard to expect an algorithm to be able to answer correctly on every input, even if it's adversarial. Here, maybe abstaining from predicting is better than giving a misclassification. And you can think in medical situations or other domains where errors are very costly, that abstaining is probably better. So this is a valid thing that an algorithm could do. And then once we have this framework, we can think of what is the loss that we would care to optimize. Before that, let me just formally just state what this looks like in this picture here. So this is going to be the more detailed version of this picture. Let me see if my cursor works here. Yes. Not? Okay, so here we'll assume that the adversary or the nature initially selects a distribution D from a distribution over the input space and chooses an F star from the function class. It's important that this F star is chosen before. In some cases, we can handle that the F star is chosen later as the process goes on. So once this is fixed, that the learner does not have access to F star, the learner may or may not have access to D. We'll talk about this when we talk about the algorithms. So what happens at every time step? The adversary decides beforehand whether it wants to inject an adversarial input. And this is denoted by if the round is corrupted, which is CT equal to 1. Otherwise, it's not corrupted, CT is equal to 0. So if CT is equal to 1, the adversary can choose any arbitrary input it wants from the input space and give it to the learner. If it's not deciding to corrupt, then the nature will draw some sample from the distribution and give it to the learner. Now the learner can decide to predict either a label or abstain. And the thing to note is that at the end, the learner will receive a clean label in any situation. So even if it decides to abstain, it will get the actual true label of the problem. Few sanity points. It's a realizable model, so there's a fixed F star that the labels are always drawn from. And this is only an insertion-only model where the adversarial example is injected before seeing the IID example. And note that here I'm not making any assumption of how many points the adversary can add. The adversary can add arbitrary number of points. So the learner must handle any number of adversarial injections. And the other thing is the learner never gets to know whether the example was injected or not. Because the learner never gets to observe whether CT was 1 or 0. Okay, so this is the model. So the learner does not actually know which rounds were corrupted. It just has to decide whether to predict or not. And in this, we can talk about what the right notion of regret or error should be. And I mean, maybe there are many alternatives, but the alternative that we went was that we want to simultaneously minimize two kinds of losses. The first is incorrect prediction. So whenever the learner does decide to predict, we don't want to make too many errors. Okay, so that's like whenever the learner decides to make a prediction, it should not be wrong. Now this alone doesn't suffice because the learner could just abstain on everything, and that would be fine. So the other thing that we want is that incorrect abstentions should be small, which means then the learner should not abstain too much on stochastic data that wasn't adversarially corrupted. So if the entire sequence was adversarial, the learner could abstain on everything. But if the entire sequence is stochastic, it should not make too many abstentions. So this can more formally be written as these two losses. which is the misclassification error and the abstention error. So what we want is that the total error, these two quantities both, are going to be really small. Yeah?
How would this be different from just not charging the learner for a like forcing the learner to classify every time, but I won't charge them for a mistake if it was an adversarial point? Is it the same?
Yeah, yeah, it's the same, but here we're asking a little bit more because the it has to abstain, right? So it has to choose that option at that point. It's not choosing a random prediction. It has to actually give a, you have to know that you're like choosing not to do that. Okay. Yeah, so it's a little bit stronger that we're asking, some certainty here, yeah. And again, as you said, here abstentions on the adversarial examples are free in this framework, which is why it allows you to handle arbitrary many adversarial injections because you're not really being charged for that. Of course, you could, if you didn't want to put an abstention, you could just predict with like, just flip a random coin and give the output. You would get an additive error in the number of corruptions that exist in the model.
Wait, I don't understand actually. So if all of the examples are corrupted, then
you can just abstain on everything. That's fine.
But you have to know to do
You'll have to know to do that because you don't know what the sequence actually is.
And you never see.
You never see.
Which things were injected.
Yeah. Yeah, you never get to see that. Okay, now you can ask this question whether, now you would think that maybe, okay, now that we can abstain, this can be, you know, the complexity is maybe the VC dimension instead of the little stone dimension because you really, like in the worst case situation, you can just abstain on everything, right? So you don't need to actually do the hard task of predicting on adversarial inputs. But then the task is, of course, the challenge is how to decide which mode you're operating in. Okay, so before I go into algorithms, let me say some connections because this has a lot of connections with a lot of things that we are discovering over time. Maybe there's more connections. So there's been a lot of work on abstention-based learning, just generally just having this abstention option in basic binary prediction. A lot of this has been studied in batch classification. So you assign like a fixed cost of abstention. So you get like some cost that's less than usually half. And then you decide whether you want to abstain, and then you can hope to get better guarantees. The main motivation for this work came from this paper, this really cool paper by Goel, Kalai, and Montessor, which was transductive robust learning. So in this, the framework was similar to what I'm describing, just not in the online setting. So what happens is that you get your training data set that's clean, and then at test time, you get to see a data set, you get to see the inputs, not the labels, which could be arbitrarily corrupted by the adversary. And you need to decide which ones you want to predict on, which ones you want to abstain on. But it's transductive because you get to see what you're going to be tested on. In the online setting, you don't get to see the future. So it's more challenging than that. But the motivation and the loss kind of comes from this model. And then again, in online classification, also there's been a lot of models that have looked at abstention. So this model called Know What It Knows, a quick model, which is pretty similar to the model that I've talked about, but it doesn't have any assumption of anything being stochastic. So it assumes that the sequence is completely arbitrary and you want to make as few abstentions and you want to not make any mistakes. And then you can relax that a little bit. But the other things that you can do with abstention is you can get faster rates, but they usually focus either on fully adversarial or purely stochastic settings. So this mix of both has not been considered in these works. Other than that, there's also like more beyond worst case things that you could think of. Here, my beyond worst case is allowing the learner an extra option, but you could imagine that the adversary instead is somehow controlled. So here, for instance, the model of smooth adversary is like the adversary injects, but then you perturb that injection. So that's one possible. Then you can assume something else about the predictability of the future, learning with some hints, and you can hope for getting beyond worst case analysis. The other thing that's probably the most relevant is adversary robust learning. So there are two kinds of adversary robust learning. You can think of test time attacks that are attacks that happen at test time. So your training data is all clean. Test time you're getting attacks, and there's like the whole literature of adversarial examples, other works. And then there's training time attacks, which means your training data set is corrupted. And a bunch of people in the room have studied models here where your training data set has arbitrary corruptions and you want to handle these corruptions. And here you can think in our model we are trying to do both, because at test time it could be corrupted and your previous data could also be corrupted and you don't know which ones are corrupted. So this is trying to handle test time and training time. However, we do get the true label every time, so we're getting some information at every time step. And the last connection that I want to talk about, which we've not explored much, but I think there might be some interesting connections, is testable learning. So this was a framework introduced in 20 by Rubenfeld and Vesselin. And here the idea is that it's not in the online learning setup, it's in the supervised learning setup, but you want to be able to have a tester and a learner. So whenever you're input data satisfies some distributional assumptions, then you want your learner to give you a good solution. And if it doesn't, then a tester should tell you that this is not a good model. And here you can think of abstention as acting as the tester. And if you take these errors into two components of testable learning, you can think of the misclassification error as soundness, that whenever you're predicting correctly, and the abstention error as completeness, that whenever the data is actually from the good distribution, you are actually predicting. So this can be viewed as an online version of testable learning.
But it seems at least somewhat different in the sense that the original testable learning framework, you know the distribution.
Yeah.
So you're testing closeness to that.
Yeah.
Whereas here, you don't know.
Yes. So very good point. Actually, for the first algorithm that I present, we'll assume that we even know the distribution, and then also it's not obvious how you would solve this problem. So in that case, then this is the same. That say you know the distribution, you're not making any assumptions on what, it could be any distribution, but you know that distribution. I actually have not solved the problem of if you don't know the distribution for all BC classes, but for some BC classes, we can get some algorithms. Okay, so these are all the connections. Any questions on the framework before I discuss the algorithms? Okay, so let's talk about algorithms. So before I'll walk you through the way we kind of thought about this problem and how we came to the algorithm. So I'll put the main result a little bit later, but I'll talk about different settings to motivate how we could try to solve this problem. Okay, so let me start with the classic example of linear thresholds, which I mentioned is hard. It has little stone dimension infinity, but VC dimension 1. So what is the challenge here? So this is the linear threshold. So you have some arbitrary threshold A. Beyond, if the number is greater than A, you get the label +1, and below you get -1. Sorry for the notation, I think I should call it 0, since I've been calling the label 0 and 1. So here you can imagine that the adversary just chooses a random A from our input line. So and then supposing these are the examples the learner has seen so far, and since you always have to be consistent, A will have to belong in between this interval, right? Because it has to be consistent with all the labels so far. Now what the adversary can do is, if the adversary is allowed to inject a random point, what it can inject is a random point between this closest positive and closest negative. Now if it injects this random point for a learner, if the learner has to predict, the learner does not really know which one it should be. So it'll try, because the original A was randomly chosen. So this is going to cause about like half of the learner will have to make, sorry, 1 second. Yeah, the learner will make a mistake with probability half if the learner has to make a prediction. Now this is the worst case situation. Now that we allow the learner to abstain, what can the learner do? One thing that you can think about, the learner can just decide that between the closest positive and closest negative, I'll just abstain. And here I can just, this is a very clean, simple algorithm, I can just decide to abstain in this interval. Okay, now what happens to the errors? So there's going to be no misclassification error in this case, right? Because you're always predicting when you're sure of the label, and you're abstaining wherever you're not sure. So the only thing that you need to worry about is what is the abstention error? How many ID examples could fall in this interval? And there's a simple argument that you can think about, that if you've seen TIID examples so far, the probability that a new IID example falls in between any positive and negative has to be less than 1/t. This is just a simple exchangeability argument. You can imagine drawing these t+1 points ahead of time and then seeing which one falls, what is the probability that 1 point falls between two selected points. And then if you sum this up over time, worst case, you are going to get only regret, that's 2 log t. So basically this gets us that the error for this kind of a strategy would just be bounded by 2 log t, which is great because we don't make too many errors on ID examples, because not many ID examples, we're not going to abstain too much on ID examples because not much ID example is going to fall in this window, and we're never making any errors, so that's perfectly fine as a strategy. And then more generally, you can think of this as a simple strategy of abstaining whenever you're uncertain. Okay, so this is called disagreement-based learning, and this has a lot of history in active learning and perfect selective classification, which is just whenever you have 2 hypotheses in your function class that disagree on a label, just decide that you don't know what the label is and abstain, and everywhere else you predict according to the consistent label. And the strategy always gets 0 misclassification error because you're never predicting, you're always predicting when you're completely certain of the label, otherwise you will just abstaining. And what you can show is that this is very well understood by this work by Haneke and like many other works, that the complexity of this abstention error scales with this notion of star number. I'm not going to really talk about what the star number is, but this is very well understood that this is tight of what the star number is. And the star number, again, is infinite for most hypothesis classes of interest. For the threshold that I've mentioned before, it is 2. So that's why we can get the answer there. So even this is not satisfying because this is much larger than the VC dimension. So can we do better? One thing that we've done so far is that we took a prediction such that we made no errors, right? Which is very strong. Maybe we can learn from errors. Okay, so let me show you another example to motivate how errors could be useful. So let's consider the class of intervals. Okay, so now just slightly more complicated than the class we had before. Now we have two thresholds, A and B. Between that, you always are positive, and outside, you are negative as a label. Okay, so here, if we went by the previous strategy, and suppose that the ID distribution had very low mass on the positive part. Okay, so the ID distribution was mostly negative. So what would happen is you would see these points that are all negative. And if you decided to predict based on disagreement, what I had before, every point is in the disagreement region because every point can have the label plus or minus because I don't know where the positive interval is. So this would predict basically the disagreement based learner will abstain on every example. And that's really bad for us, right? Because we're just going to abstain everywhere, we're going to get very high error. What can you do? So a simple algorithm that you can think about is that whenever you are in between two negative examples, predict negative. Whenever you're between two positive examples, predict positive. And when you're between a negative and a positive, abstain. Okay? So what's going to happen in this example, I'm going to just predict negative everywhere. Why is this useful? The moment I actually, so with this strategy, the misclassification error will not be 0 because of course like there's going to be some positive examples maybe the adversary puts in or maybe the true distribution has that I'm going to make an error. But what happens is that if the algorithm makes an error, it learns something, right? So what happens if the adversary gives a point in between, it suddenly learns a positive example. So now we know that whatever the version space is left, that has VC dimension only 1. That VC dimension has been lowered and it's just 2 thresholds now. Because I know where the positive point is. Now everything else is not in the disagreement region anymore. So now I can start predicting based on that. And what this gives you is that now it reduces to the 2 threshold problem that we had before. So that only has the chance of ID points falling there again is 2 log t. And you make only one misclassification mistake. So what this says is that mistakes are actually helpful for learning. So you can actually do better than the star number guarantee that you would get by the basic disagreement style learning. And there's some way that you have to figure out. So now the challenge is like when do you figure out that this point is actually going to be helpful for me to make a mistake on and whether it's not going to be helpful and I should just abstain on this example. So that's the main challenge. And these were the 2 examples that kind of motivated us to think about like, okay, there is some way to decide when we are getting some information gain and how do we do this using only like this one sample testing. So now I'm ready to present like the main results that we have. So this is the first result that we have. This is assuming access to the marginal distribution. So this requires knowing what the marginal distribution is, so knowing what D is. What we can show is that for any class that has VC dimension D, you can achieve the following guarantee. The misclassification error will be bounded by D square log T, and the abstention error will be bounded by D, 6D, some constant times D. Okay, so this is the guarantee we get. And this works even when F star is adaptively decided. So the adversary doesn't have to choose the F star ahead. It has to just make sure that everything till now has been consistent with the function. So there has to be some true F star. Some things to note, the misclassification and abstention error are different by a factor of D. Our strategy, we don't know how to improve that D square. I don't know if it's necessary or not necessary, but this is what we can get. The second result that I'm not going to talk about much, but just to say that this is actually possible even if you don't have access to the marginal distribution. What we can show is for VC dimension 1 classes, there's an algorithm that pays a much worse regret. So you get like 2 square root t log t. So there's an extra square root t factor in both the misclassification and abstention error, but this does not require any access to. So you can use your past data to try to make an estimate and decide how to predict. And this uses really the structure of VC dimension 1 classes. And there's this really nice tree characterization of VC dimension classes by Scheib and David from 2015, and that's what we use for this. And we can also actually extend this to axis-aligned rectangles and some other special classes, but they all require using the structure. So this is quite open, like what you can do without access to the distribution if you don't, for general VC classes. Okay, so these are the two main results we have, and I'm going to give you some intuition of the algorithm for the first part. That how do we go about making this decision, and it's kind of going to be motivated a little bit from the example of the intervals that I talked about, where we are deciding when to make a mistake. Yeah.
You get the label if you abstain.
Yeah, you get the label when you abstain.
So the previous example, when you're deciding to make a mistake or not, does it matter if you make a mistake to abstain and get the label?
Yeah, so I think it's important that we predict, because if we didn't predict, and so if you predict and you're correct, you don't suffer a loss. But if I abstain, I always suffer a loss. So it's very important that I decide to predict, because on ID examples, I want to predict. That's why it's not, yeah, it's important. Yeah, good point. Okay, so the idea comes from this notion of disagreement coefficient, but like looking at higher orders of this disagreement quotient and using that to figure out whether we're uncertain and whether we're going to get a lot of information if we make a mistake. Okay, so what is this higher order disagreement? This is really exploiting the property of VC classes. So if in VC classes, like one of the way VC classes are defined based on the property of shattering, which means that given a set of points, can you assign, are there functions in the function class that can assign all possible labels to this function class? Then we say that that set is shattered. So you could define this shattering, so disagreement you can think of as like take only one point and decide whether it can be shattered, which means can it have both labels? So that means there's some classifier that disagrees. Yeah.
So if I don't give you the label when you abstain, will wait?
They will. Because I won't know that that was a positive, so I don't really learn anything from my mistake. I don't really make a mistake. Yeah, it's a good question. What's going to happen if I don't get the label? Yeah, I mean, I'm not going to learn anything, so I'm not going to make that much progress. So it might eventually hurt me, at least in the algorithms that I have in mind.
What if they just can query the same point again, maybe if they were right?
The adversary can keep putting the same point again,
right.
but then maybe my algorithm
then
will
you
be
would
smart to
know,
just
right,
always
you can
abstain on that point.
Oh, okay.
Yeah. So maybe it's possible that these algorithms can be fudged into that. We didn't think about it actually, but good question. Yeah.
Do you know as a confidence that whether you should predict or you should abstain, like a probability that you might be correct because of that probability?
Yeah, that's kind of how the algorithm will work, basically, that the algorithm can't really actually know whether this point is in distribution or out of distribution. It'll create an estimate and just go according to that estimate. Oh yeah, I'll just talk about it in a second. But it is a determinant.
Like the lower bound you had in that case, like each of the hypotheses have different regions where they're uncertain. So somehow like most of the hypotheses know what's going on. Right?
Yeah. That's kind of the idea. So in the interval thing, you could think that if you had 2 points and you were looking at disagreement of 2 points, there you would be very sure now, because not many hypotheses can disagree on that. Yeah.
Do you know any lower bound showing that this log t or root log t is necessary in the bound?
No. This is like really open. I don't know anything about many questions are like, I don't know how to do this at all. This is the only pause. I'm just mentioning the results we could come up with. So yeah, I'll talk about the open questions at the end. So here, okay, let me define the shattering probability. So what you can define the shattering probability is that take any random set of k points from your distribution and see whether the function class shatters them or not. And then that can give you a natural notion of the probability that any random points drawn from the ID distribution are shattered by f as this notion rho k of f. And you can think of this as that this is kind of measuring what the different levels can tell you which level of complexity your version space has. Because say that you've like learned something about your distribution, if you start at the original point that when you have no information, then a lot of points should be shattered at level d, which is the VC dimension. Because that's a VC dimension, many points can be shattered there. And the more you learn about the function class, you should be shattering at a much lower level. So this is kind of measuring which level of complexity your distribution actually comes from so far. Some things to note about this is ρ1 is exactly the density of the disagreement region, which is just whether you draw a point, whether it can be shattered by the function class. And this thing is reduced. So rho k is going to be greater than rho k plus 1 and so on, because if you can shatter k plus 1 points, you can shatter every subset of those points as well. And rho d plus 1 is 0 because you can never shatter d plus 1 points. So there's no draw that you could get that could shatter d plus 1 points. Okay, and this was used, as this was proposed in some active learning framework, where they use this to decide which points to query. but not in this context as far as I know. Okay, so now the algorithm is the following. You choose a level k. This is, I'll make it more formal right now, I'm just giving the intuition. To make a prediction on the current iterate, you get that iterate. You compute the k shattering probability for the current version space that you have with the restriction that this x hat t is labeled 0 or labeled 1. So you get these two numbers based on if you label it 0 and label it 1, what is the remaining subspace, how much information would we have in this space. If both these quantities are large, we just abstain. Because this point is not really going to give us a lot of information about the true distribution because both these quantities are large. Else, we predict according to the larger one. Okay, if you predict according to the larger one, what's going to happen is that if you make a mistake, we'll go into the smaller case. So we're going to gain some information from this mistake that we make. So this is analogous to like halving, which you might have seen before, that this is like, okay, this is an idea that you could think about. Every time you're going to reduce something by a constant factor, so you cannot make too many mistakes. And here the hope is that for IID points, these quantities can't be very large very often because you're getting information each time you're getting an IID point. So it cannot continue to be large. So this, not too many IID points should fall in that region. So that means you should not be able to abstain on too many IID points. And then of course we have to deal with these levels, and after these quantities go small enough, we can just go down a level because that means that we saturated that level. Our actual distribution is actually at a lower level than we thought originally. Okay, so in the interval case, you could be like starting when you only see negative points, you're at the level 2 because that's the VC dimension of that class. But the moment you see a positive, you've gone down because now you're just looking at thresholds. You already know that the version space that's left does not have VC dimension 2.
So what's the intuition for IID points? These points can't be very large very often. I mean, somehow it has to do with how the shattering probabilities.
Yeah.
They're a conveyor belt. Right?
Let me explain that. Like I just have a lemma to explain that. So I'm just going to formally write this algorithm down. You cannot read this, but basically we check whether this quantity is greater than. So this might answer a little bit of your question. So we check whether it's less than 0.6 of the shattering probability of the function class that we have currently, and then once this goes down enough to some threshold alpha k, we go down a level. Okay, so what happens is internally, whenever we're inside and we've not gone down a level, rho k is always going to be larger than this alpha k. So we're going to know that rho k plus 1 will be larger. So we know rho k. So we know that there is some information in this level whenever we're in this level, and we've gone up from the level above. We know that the level above has very little information. So we have this gap always. That is what is going to give us the fact that the IID points have no probability, and this can actually be defined in this lemma that I might not have the time to actually go through the proof. But basically what it says is, for an IID example, the rho k, if I label it 0, plus the rho k if I label it 1, being greater than 2 times eta for any function eta, so in the previous one I put 0.6, rho kf is bounded by the ratio that this is telescoping. So because of we're going on levels only when it goes down, this number will remain small. So that's basically, and the idea, actually the proof is very simple. It's just like using the fact that shattering, if you're shattering a point x, this rho k of f of x going to 0 and rho k of f of x going to 1 is basically like, could you shatter these points without this x between these two function classes, and the probability that you could shatter with both these function divisions. And then you take the expectation and use the Markov inequality, you will get this condition. And this basically gets us that you can't abstain too much on IID points. However, every time you make a mistake, you are reducing rho k, and you can't reduce it too many times either because then you'll have to go down a level. So that basically gives us both these error bounds. And let me see if I have, okay, I guess that's all I had for the technical content. I finished a little bit too early. So that's basically the idea of this. I don't have the slides to talk about the idea for the VC dimension 1 class, but let me mention just a high level idea. So let me go back to the algorithm. So what the algorithm needs here is to estimate this quantity rho k for which we were using the distribution, right? So what you could imagine is that if you didn't have the distribution, what you could do is you could look at all the data that you've seen before and do an estimate, like a leave 1 out or leave k out estimate using that data that you have in the past. So what does that mean? I just remove k points from the previous distribution, whatever points I have. I see what the function class I get from the other points, and I decide whether these k points are shattered by this or not. And that can be thought of as a rough estimate of approximating rho k, but we need that to be robust because we have adversarial points even in our input. So in the VC1 class, what we can show is that we can compute such an estimate, and that is robust to our errors. And that's why we're able to get this algorithm to work for VC dimension 1 classes. VC dimension 1 classes have a lot of structure, which is not true for other VC classes. So we don't know how to make this work, but this is a potential way that maybe this algorithm could still work if it doesn't have access to the distribution. But here it heavily relies on the distribution. Okay, so I'm going to conclude. Any questions before I conclude with open questions? Yeah. So basically what happens is that we run this at different levels, but once we reach level 1, where we've gotten that we're pretty much in that state, and now we can just abstain on anything that we disagree on, and we don't have to do anything more sophisticated because the remaining function class in our notion has very low VC dimension. So at S1 is just the disagreement region. So once we've reached there, we just disagree. We behave as the algorithm that the threshold algorithm was, where we just disagree wherever we're not sure. That's just a corner case to handle that. And the other thing that's important is that the thresholds that we maintain, because we want these ratios to be small, have to be scaling as t to the minus k, which is why it's very hard to actually do this with samples, because we want these thresholds we don't have that many samples to actually estimate them. Any other questions?
Do we know how to compute this row k
Efficiently? Not really. Like for half spaces, you can imagine constructing like a linear program and then trying to do some sampling kind of techniques to estimate.
But only gives an error, maybe approximation, but not the exact value.
Yeah, and we need like very close, so I don't know how to do that. But like for the VC1 class, the algorithm that we have, that's actually efficient. Because we use an ERM, kind of an ERM style oracle to like decide to estimate these things, because that's only a leave one out estimator. Leave k out, you need to see all possible sets of k and how they're shattered, which gives this exponential time in k.
So actually, I have another question. So, do we? Is it help if idea after every sample, if we make the prediction, we know whether this is the sample from a stochastic
Yeah.
or adversarial?
Yeah, so that's actually going to help us, because now we can construct these estimates using all the data that we have seen before, and we can get some errors on that. So the reason, why we can handle this t to the exponent is because we can take like all possible subsets of size k, which is going to be like t to the k subsets in the history, and then we can use some U statistic kind of bound to like maybe say that this concentrates. So it's probably possible to get that to work if we know which ones are not corrupted. If they're corrupted, then all things are off. We need a robust estimator for this thing.
Sorry, can you relate this to margin? Like if you're closer to margin, this happens if you're somewhere in between the other part of the algorithm?
Yeah, so I don't know how to view this as exactly as margin, but you can think of this as, if you're at level k,
Is k equal 1 closer to margin than like proximity?
so k, you can think of this as like, k is like maintaining what the VC dimension of the remaining class is. So when you assume margin, you're assuming implicitly that the VC dimension is kind of reduced and depends on the margin that you have in the problem. So here this is like, can be any function class, might not actually have margin. So it's not exactly a notion of margin.
Margin is not the right word, maybe boundary on decision. Like you have a set of decision classes and those who are like boundary.
Yeah, so I guess if any of these quantities is very large, like the rho k ft of x hat t goes to 1 or x hat t goes to 0, if any of them is really small, that means that we have a lot more information about this label. This label is being consistent with reducing our uncertainty. So maybe this is like some notion of margin of how confident you are of this example.
So where is k equals 1 in that setting? Like if I want to think about it intuitively, where is k plus 1? How should I think about k equals 1?
How should you think about, sorry?
K equals 1.
Oh, k equals 1 is just like, at k equals 1, you're just in that threshold example that you can think of, that you're just basically deciding whether you want to predict on this example or not predict on this example. And here you're like, okay, whatever I'm not sure on, I'm just going to not predict.
I think it seems difficult to connect this to like something geometric like margin, because I mean, to me, the row Ks, they look a bit more like sort of amortizing the costs of a game.
Yeah.
Because like the examples you had, right? I mean, the uncertainty region is everything with those intervals, right? But then if you make a mistake, you're done because you know where the interval is. So it's more like creating a charging scheme for like how you're reducing
you pave the future.
A smooth notion of the VC dimension.
Yeah. Yeah, that's the right way to think about it, that every time you're at some level, each mistake is giving you some guarantee in the future that you're going to make less mistakes. And so we have to pay a lot in each level and then go down every level. And you might not actually, like, maybe you'll just stay stuck at one level at some point also, because there might not be any way to go down that level with the information that we have. So it's not exactly so clear, but we can talk offline about this. I'll just end with some open questions, because there are a lot of open questions. General VC classes without distribution access, we don't know these results. Our current, there's the natural leaf K-out estimator, but I don't know how to prove that with adversarial corruptions it's actually a good estimator. So maybe some ideas there would be useful. Maybe in other places people have estimated these quantities. In conformal prediction, I think they kind of estimate these, but they have this exchangeability that we don't have because we have corrupted examples. Beyond realizability, I assumed realizable, and that was very important for all these arguments. So if you have even a slight amount of label noise, what happens? Don't know. Beyond binary classification, so the one good thing that this algorithm has is not exactly using uniform convergence, which kind of fails in multi-class and partial concept classes. And since this does not use it, that's a natural extension. We have not worked it out, but maybe we can handle more complicated, like multi-class situations or partial concept classes where we don't have access to the entire space. So that might be possible. Computational efficiency that I never mentioned at all. If we can get computational efficient versions of these algorithms, or there are some statistical computational trade-offs, it's not even clear. And that d-square factor, that even for the statistical, is it tight or not? Is there something that you lose for the certainty? It's not clear. And last, like, there are connections to these techniques like testable learning, conformal prediction, SOS style robustness, because SOS kind of tries to predict, use these indicators to find out which ones are corrupted, so gets this kind of guarantee. So maybe some kind of robust estimators we can use to construct all these leaf K estimators using some SOS techniques. So maybe even understanding for half spaces with Gaussian distribution, how you can learn this is already an interesting question. So I'm going to end with that, and I hope I convince some people to at least think about this problem. It'd be great to know the answers. I have tried a lot, but I don't know these answers. Thank you.